Great. Thank you.
All right, so kind of total price, we'll go ahead and get started. My guys will be the Alice in front of the Canadian education team for MITEC. And it's for attending one of our speaker series where we cover some of the cool climate tech research happening with this. And so today's speaker is Charles Dawson. He's a fifth year PhD in the aeronautics and aeronautics department here at MIT. And so his research is focusing on helping engineers design, deploy, and debug autonomous systems. And today he's going to be speaking about some of his research figuring out better failure prediction modeling and electric grids. So
Great. Thank you, Alice. Great. So I know we have a more general audience today, so I'm hoping to keep this talk more high level and keep it around 30 minutes so we have plenty of time for discussion at the end. So like Alice said, I'm going to be talking about failure prediction in electricity markets. And just to set the context, we live in this time of great energy abundance, but sometimes it can be easy to forget, easy to take for granted the infrastructure that is actually providing that abundance for us. So does anyone recognize this picture? Anyone tell me like where this is?
I guess Texas maybe?
Yes, yeah, this is Houston before and after the winter storms in 2021. You can see the blackouts in various parts of Houston. This was a lot of factors contributed to this. I'm sure many like master's and PhD theses are being written about what went on during the storm. But a number of generators froze at a high level and caused the grid operator in Texas had to shed a lot of load. It's led to a lot of outages. I think almost 10 million people lost power and between 200 and 300 people died as a result of this event. It's not just in Texas. In 2017, Hurricane Maria hit Puerto Rico and had substantial, very significant human loss, but also very significant damage to the energy infrastructure on the island. And this is damage that they're still recovering from, years after this event. But you can see like these night sky photos really show the damage to electrical infrastructure. And this is one of my favorite photos because it kind of boggles the mind to have a puzzle piece chunk taken out of North America. But this is the 2003 Northeast blackout. I think 55 million people lost power in this event, including all of New York City. And like, there are a lot of scary things about a picture like this, but the root cause of this event was 3 transmission line failures and 1 software bug that prevented the system operator from reacting to those failures in time. So 3 cascading failures somewhere in Ohio that caused 55 million people losing power. And society really depends on electrical power to function. I mentioned that Manhattan lost power. People were trapped in the subway system and had to be rescued. Everyone who commutes to Manhattan by rail had to walk home that day. So this is the view of those people walking home over the bridge the day of the blackout. And this is the New York City skyline after that event, where the only light here is from the cars, which I guess are getting their electricity from gas. This is also, of course, not just a US problem. Earlier in 2023, there was a blackout that affected all of Pakistan. This is 230 million people lost power as a result of this event. This is Karachi. There's buildings all over here without any lights on. Those lights, again, are coming from the vehicles in the streets. So hopefully this has all helped convince you, or maybe you're already convinced, that the electricity grid, incredibly useful, most of the time incredibly reliable, but it is vulnerable to these disruptions. The tricky part here is that let's take the North American electric grid as an example. The North American electric grid is one of the largest and most complex machines ever built by humanity, or I guess it's 3 machines, depending on how you split it up, Northwest and Texas, East-West and Texas. This is an incredibly large and incredibly complex machine. No one person can look at this map of high voltage transmission lines in this example and figure out where are the critical vulnerabilities in the system. Even if you break it up and just look at, say, like New England ISO territory, that's still a huge system, incredibly hard to do this analysis of looking for vulnerabilities so that you can protect them. So I'm going to be talking about today is contingency analysis. So how can we automate this process of discovering vulnerabilities in the power grid, and then automate the process of repairing those failures to make the grid more resilient. So why do we care about better contingency analysis? Well, one first answer to this, which is in the title of the talk, is that contingency analysis is at the key of a lot of market operation. So when market operators are clearing electricity in the day-ahead markets, they are making sure that electricity is not only low cost, but also deliverable from all of the generators, all of the demands. And there are reliability standards in the North American markets that say that when you do that process, you need to make sure that you're resilient under, like they call N-1 failures, where the operators are essentially looking at all these predicted contingencies and saying, can I deliver electricity in these different failure case scenarios? So if you're not covering all of the possible failure cases, or if you're being too conservative, there are issues with both of those in terms of the efficiency of these markets. And I think we're seeing this manifest now in, for those of you who are following the interconnection crisis, a lot of the network upgrade costs that are blocking interconnection requests come from the need to upgrade the grid to handle these contingency scenarios. It's not that the solar power isn't deliverable in a standard situation, it's that it might not be deliverable in some contingency. So if we can improve how we model and react to these failure cases, we can get more efficient electricity market. Another example is with infrastructure planning. Is anyone following PG&E's undergrounding plan? I think they had a plan to bury 10,000 miles of transmission and distribution cable. If it is approved and executed, it'll be the largest undergrounding project in the world, with a $6 billion cost. So the question is, how do you identify which lines are most vulnerable? You know, if you only have a fixed budget to do your undergrounding, how do you spend that budget in the optimal way to, protect the grid given the budget that you have? And finally, if we have a better way of understanding where these failures are, we can better react to disasters or failures of the grid. So this is pretty common in places like Florida, where they have regular severe weather. Grid operators will pre-stage repair crews throughout the state in areas that they know are going to be vulnerable. So if we have a better understanding of where those vulnerabilities are, you can better dispatch those crews so you can get faster response times and fewer outages for the customers. Okay. So contingency analysis, it's important, but how is it done today? And what are the issues? Like I said, electricity grids are incredibly large, complex, interconnected machines. Looking for these vulnerabilities is like trying to find a needle in a haystack. The first option that you might consider is you just check all of the failures. So if your system is small enough, maybe a microgrid, maybe a small municipality, maybe you can look through all of the possible combinations of failures. But this isn't really going to scale. When I talk to people who are running interconnection studies, they talk about having to run through thousands or tens of thousands of different contingencies in order to check whether electricity is going to be deliverable. And when you have to do that, it means that the studies are going to take a lot longer to complete. They're going to be a lot more error-prone and manual. And so it really takes too much time. The second option is that maybe we don't need to check all of the possible failures that could affect the system. Maybe we can get away with only checking the worst case failures. And also, please, I know that the screen might be hard to see from there, so feel free to move over here. Like, don't worry about disrupting anything. So we can check only the worst case failures. And the idea is that maybe we can focus in on, we don't have to check every line. Maybe there are a few critical vulnerabilities. Then the question is, how do we find what the worst case failure is? I'm going to talk about how some of the existing methods for finding this worst case failure can miss critical vulnerabilities in electrical systems. And then I'll talk about how our lab is proposing methods that can answer this question more efficiently, so faster, and also provide better coverage of the range of possible failures that we might see. And like I said, this is where our lab comes in. I work in the Reliable Autonomy Lab at MIT. We're based in Aero, Astro, and Lids. And our mission in the lab is to design safer and more reliable control systems for autonomous systems. And we're going to be drawing on tools from machine learning, optimization, control, and formal methods to make this happen. Some of our past projects in the lab we worked on everything from satellites to autonomous vehicles to fighter aircraft and robot manipulators. And we're recently trying to apply some of the tools we've developed for these robotics concepts to power systems and these interconnected problems that we see there. So just to give a quick overview of what I'm going to talk about, I'll start with the state of the art. So how do we do failure analysis today and what are some of the issues? I'll talk about how you can get some tricky issues of false confidence if you rely on some of the existing methods. I'll talk about the methods that we've developed for prioritizing a diversity of failures and getting better coverage of the range of things that we could see happening in our system. And then I'll show how when we're able to better predict different failures that can affect our system, that does actually translate to more resilient, more reliable operation of that power system at runtime. So how is this done today, right? I mentioned finding a needle in a haystack, zooming in on option 2, where we have this idea of, okay, we don't need to look at all of the possible failures. We only need to look at the worst case failures. One way that you might start by doing this is through using something called, just use any optimization tool, right? Pick your favorite optimizer. You say, we have some measure of reliability. Maybe it's amount of load that we have to shed, and we try to maximize that quantity. I have a cartoon here of what that looks like. Is you might start by looking at one particular transmission line and seeing how does the system react if this line goes out, how much load has to be shed in this case. Then you say, okay, what are nearby failures? So you can make small changes to your solution and say, okay, if I move over here, I'm going to increase the amount of load that's going to be shed. And you can keep doing this until you converge. So you find some area where no matter what you do to change your solution in this area, you can't make the situation any worse. So you can't cause any more load to be shed. And what this corresponds to in this cartoon illustration here is that if we're doing some optimization problem of our, just say it's a cost function, we're trying to minimize it. What this is doing is we're stepping along this landscape until we get to a place where we can't improve. Those of you who worked with optimization tools before know the other side of the story, which is that this is a very local process. When we converge, we're not saying that we've necessarily found the globally optimum solution. We've just found some local minimum or local maximum in our cost function. There are, of course, global optimization tools for addressing this, but at a huge cost of increased runtime. And this plays out pretty commonly in electrical power systems. If we look at this particular IEEE test system, and we look at what the true worst case failure is, it's actually going to be a combination of these two lines failing at once. And that's something that we're not able to find, even with multiple random restarts of these local optimization methods. It's not something that we're able to find in existing approaches. What does this mean for the reliability of the system? Well, if you haven't found the true worst case failure, then if you prepare for that, you're not actually preparing for the true worst case, and you're going to be surprised in an unpleasant way when it comes time to actually run that system. So if we compare the predicted worst case, so if we run this local optimization process, we converge to a set of locally optimum failures, and we run this, we repeat this randomly 10 times to try to get some diversity, and we optimize our electrical dispatch against those predicted failures. We can see that if we actually run that dispatch through 1 million stress test cases, 17% of those cases are going to be more severe than what we thought was the worst case. So when we use something like this local optimization method, we're going to be, falsely confident in how robust our system is, because we thought that we've prepared for this one worst case, but in reality, a lot of the cases that we're going to encounter are going to exceed that worst case. So I've talked about how some of the existing methods can struggle to find, the true worst case failure. Next, I'm going to talk about the methods that we've developed in our lab for helping to address this issue. The headline here is that we have a method that, instead of just prioritizing the severity of an outage, is also going to prioritize generating a diversity of different failures. So failures that affect a diversity of different components in your system. And we'll come up with some very efficient sampling-based algorithms for generating those diverse failures. Taking a step back to the higher level, just to get some theoretical inspiration for where our approach is coming from, we're going to start from a grounding in computational statistics, which this might seem like a little disconnected, but it'll join right back up in just a moment. So the question that I want to ask is, what is the best way to represent a probability distribution like this Gaussian, right? One option that we can use is we can represent this distribution through its mean, right? So we can find the highest likelihood point on this distribution. The analogy to our optimization problem that we were looking at before is finding the mean is kind of like finding the local optimum of some cost landscape. So we're just finding one point, it's kind of peaky, and we're going to use that to represent the space of things that happen. Another way that you could describe this distribution is with the mean and the standard deviation. So in the case of a Gaussian, it is like perfectly defined by these two pieces of information. If you know where it's centered and you know the amount of spread, that defines a Gaussian. But if we wanted to think about more complicated shapes, so optimization landscapes or probability distributions that have maybe multiple modes, just the mean and standard deviation aren't going to be enough to accurately represent the space of things that can happen. I would argue that the most fundamental way to represent a probability distribution is through the events that it generates. So what is the space of samples that we can draw from this distribution? And this is nice for three reasons. First, it can represent any distribution. So it's not only representing one Gaussian, but it could represent the range of things. For example, like the range of failures that we might expect to see in the power system. The second reason that this is nice is it gives us some sense of the risk of these events. So we can look at the scatter plot of the samples that we're getting, and we can understand what are the risks that are incurred in those different scenarios. And another benefit of this is that it does cover extreme events. So you are able to draw samples from the tails of these distributions, which can be key to understanding the reliability of certain systems. So how does this connect to what we were talking about before? When we talked about looking for these failure events in power systems, we were talking about that through the lens of optimization. So we're trying to optimize this function, take these local steps to find a solution that can't be improved anymore. There's a nice trick that we can do where we take this optimization landscape and we construct a probability distribution that is analogous to it. And what we've done here is, because this is a minimization problem, we take regions that have low cost in the optimization problem and assign them high probability in this probability distribution. And we give low probability to events that are high cost. And so what this would mean is that if we're looking for failures that minimize this objective, this is a distribution that assigns higher probability to the failures that we are looking for. Of course, this is not a Gaussian. It's not going to be any sort of distribution you can look up in a textbook. And that means that there's not a simple Python function that we can call to sample events from this distribution. What we can do instead is implement a class of algorithms called Markov chain Monte Carlo methods. And what these are going to do is they're going to generate individual samples in a series. And if you run this series for long enough, you're going to approximate drawing samples from the entire distribution. One of the benefits of these methods is that you can apply them to a really broad class of distributions. There are a lot of tricks for speeding them up, and you can actually use the gradients of this distribution, which we rely on a lot to do really efficient sampling. And what we're going to do here is that, whereas in the optimization setting, we were just locally improving our solution until we converge to a local minimum, and in this case, we're unlucky and we missed the true global solution. When we move to this sampling approach, we're actually able to generate samples that move back and forth across both modes of this distribution. So as we draw samples, we get coverage not only of the true optimum, but we also get coverage of the other mode, which is important for getting a diversity of solutions. And the average of all of these solutions, which is the red dot, the average is going to approximately recover the global optimum as we run this algorithm for long enough. So what we can do is we can take this approach, this reformulation from optimization into sampling, and we can apply it to this problem of searching for failures that are maximally disruptive to an electricity grid. And when we do that, we can draw samples from that distribution. So we can get a range of diverse failure examples that all lead to a high impact on the system. And if we look at the failures that are generated for this, there are a lot of nice insights that we can pull out of this, simple test system. An example would be like, okay, this generator here, it's kind of off on its own, disconnected from the rest of the system, except for one power line. And we actually see that, a lot of the samples that we draw from this failure distribution do target the connection between this generator and the rest of the grid. Another example of why this is nice to get the diversity from these different solutions is that we do have this solution that we saw earlier where this one power line is out. And when that happens, you do see some minor decrease in the system performance. But actually, if you combine this failure here with a failure on the other side of the system, then you get total voltage collapse to your system. So you only get full system blackout if you combine failures in different sides. So the benefit of our method is that it's able to efficiently explore the space of possible failures, and it can discover all of these different issues, which might be kind of hidden just over the horizon in a local optimization setting. Finally, just like to close of we can generate this diverse set of possible failure cases. Now what does that give us in terms of operating the system more efficiently? So if we revisit the same experiment that we had earlier, where we generate this diverse set of failure cases for our network, we optimize the generation dispatch to deliver power to load under that range of possible failure situations. We find that optimal dispatch and we test how it performs on 1 million random trials. We can compare the range of failures that we see in our predicted set of worst case failures to the actual range of behaviors that we see on this test set of 1 million examples. And now, whereas before, our predicted failures weren't really covering the range of behaviors that we saw in practice, now we're getting full coverage of the range of behaviors that we do see in practice. So this gives us some confidence that we have in fact discovered the true worst case, and we're less likely to be surprised when it comes to running this dispatch on a system. Another benefit here is that we've also shrunk the range of performances so that our tails are a lot lighter here. If you recall in our previous example, we had this long tail of bad behaviors that we could see from our system. When we optimize against this more diverse set of test cases, we actually compress those tails and we capture more of the possible behaviors in this central node. And that's beneficial because it just means that we're less surprised. There's less variation in the range of behaviors that we'll encounter when we deploy this dispatch. And if we compare the types of failures that the two dispatches are susceptible to, so the case that's optimized against the test cases that we find using state-of-the-art methods and the test cases that we find using the failure cases that we find using our method, we find that the state-of-the-art method where we use adversarial optimization to generate these failure cases is going to be relatively susceptible to failures at all levels of number of affected components. So we have a relatively large number of single faults, double faults, triple faults, and so on. When we're able to optimize the electricity dispatch against this more diverse, more representative range of example failures, we actually reduce the number of failures that we actually experience across the range of fault levels. So we see fewer single faults, fewer double faults, and fewer triple faults. And this is another benefit of our approach. Might be a little bit in the weeds, but we're not really limited to n-1, n-k. We're looking at a range of different failure distributions. Great, so I've talked about the existing state-of-the-art. How are these contingencies predicted using optimization-based methods? And I've shown some of the issues you can run into there. I've talked about how our method proposes a way to add diversity into the set of sampled failures. And I've also shown how that leads to more robust, more resilient dispatch of electricity in our example case. This is my last slide. I'd just like to conclude by talking about so what. I think it's not a surprise to anyone in this audience that there's like a crisis of faith in the electricity grid. People are talking about multi-year wait times for interconnection of new renewables, over 2 terawatts of renewables waiting for interconnection across the US, and all of these incentives that we're seeing going towards clean energy and the energy transition might not be realized if we don't improve the way that we manage and invest in the electricity grid. I think that there's a strong need for better grid analysis tools and better grid control tools. And what I'm trying to push from our lab's research is that we can transfer technologies that are developed for robotics, autonomous systems, and AI into the energy systems to meet this need. This is my contact information. I think it's also on Kerberos, MIT Slack, and everything else. Hopefully we have plenty of time for food discussion and any questions that you might have. Sure.
Yeah, no, thanks so much. Super interesting. When you showed this to the system operators, what did they say? I'm just curious, sort of the transition is also about utilities as organizations and how they function.
Yeah, that's a great question. We haven't shopped this to any system operators yet. If you know any, I would love to talk.
You might want, yeah, we should.
Okay, yeah, that's great. I was just at NAPS 2 weeks ago, so the North American Power Symposium, presenting this work and getting feedback from the power systems community. I think they are interested. The main issue that we have right now is like engineering effort and scaling it up. So we have these small test systems, like 57 buses. We want to get to at least 1,000 before we can start looking at practically sized systems. I think that's a lot of engineering effort in terms of like Python to C++, just writing the code to be more scalable in that sense. Yeah, but I think that the trend that I'm seeing is that a lot of system operators kind of at all levels are concerned about how they are going to transition to more renewable electricity without compromising the reliability standards of their systems. And so we think we need tools like this that can really focus on reliability as well, but we should talk.
How do you draw the samples? Do you just do all the simulation or just expect that it just also applies to the real grid again? Or how do you do it?
Yeah, so we draw the samples by using a simulation of the power flow through this network. So we have a description of the network, like the connectivity between all of the buses and the impedances as well. We solve the power flow problem. We actually solve it in a differentiable manner, so we get gradients through that solution. And we use the gradients of that simulation to simulate more efficiently. If you weren't able to simulate, you wouldn't be able to generate as many samples, so it would be a much slower process.
And you think that would also generalize to the real grid at the end?
Yeah, I think that in the case of electrical flow, I think the models are fairly good. There is this question of like, how do you get this data? Like it's like confidential energy infrastructure data. But once you have the connectivity and the impedances and everything, then I think the transfer should be relatively straightforward.
So this is really awesome. Thanks so much for the presentation. One thing I'm curious about that maybe I just didn't get is, so you're identifying the most extreme cases of failure. What is the trade-off between that and identifying the most likely sources of failure, which like seems like it was more of an anomaly detection type application. So like I'm curious, yeah, how do the two connect or translate?
Yeah, that's a really good question. So something I didn't get into in the talk is that as we do this sampling process, we actually start by sampling just like the most likely events that can happen in the system. So we start with a prior distribution over the different behaviors of all components. We start just by drawing a bunch of samples from this distribution of things that are likely to happen. And then as we progress, we gradually turn up the volume on this severity measure. And so we're going to gradually step from things that are just likely to happen to simulating things that are likely, but a little bit more severe. And then eventually we're just simulating things that are severe with some regularization for making sure that it's not just like all of the lines have gone out. But we are kind of like interpolating from likely failures into more severe failures to try to balance this. So that was so let's see, this guy. Yeah. So what this is plotting is we just generate like a random set of 1 million grid configurations essentially, and then we filter by which of those configurations are causing a failure, and then we just observe the number of lines that are out in each of those failures. So the shape of this distribution is just given by like the way that we've modeled things. We assume like that there is some like each line has some like 0.1% probability of failure. That will just like average out to a shape like this. So, like you're very unlikely to see 10 lines out just because it's like a conjunction of a lot of events.
Now, first, when you do the sampling, when you do the sampling, how many samples do you make relative to a 20 samples?
Yeah, that's a good question. So as we run the MCMC, we're doing, if we say we want to generate 10 samples of different failure configurations, we'll run 10 parallel chains of MCMC. And we're usually running for like somewhere around 1,000 steps in each of those chains. So each step, you're in theory generating a new sample, but steps that are right next to each other, the samples are highly autocorrelated. And so if you want, like we want diverse failure cases to be generated, so we want low correlation between our samples, and that's why we have to run these independent chains. if we were to just draw samples from the same chain, there's a risk of like the correlation would be too high. Yeah. There are also like a bunch of MCMC tricks that we can talk about too.
So you noted that like there's still a bit of work in terms of like making the code, like moving it to something that would be feasible for like a grid house or whatever. Is that something that besides like changing the code base or whatever, is that something that you would like say is feasible given like the computational complexity of like it's
Yeah, so that's a great question. I think that we're optimistic that it will scale well. I mentioned that we're transferring this from other like robotics cases. When we've looked at robotics failure testing problems where we're looking at like 1,000-dimensional space, and we're trying to find failures in that like 1,000-dimensional space rather than like 80 to 100 in the these like simple test networks. It does scale pretty well. The theoretical argument there is that we're using these gradient-based MCMC methods. We're using like metropolis adjusted Langevin. There are some results that, depending on your problem setting, you can get really good like polynomial dependence on problem dimension. And we are optimistic that we're satisfying all of the assumptions of that theory. We have to regularize the problem to make sure we get the benefits of that theory, but we are seeing like pretty strong convergence rates, especially as we scale problem dimension. One specific issue with this is that we're trying to do this in a differentiable manner, so we get end-to-end gradients. That means we need to solve the power flow equations in a differentiable manner. Currently, like we just like solve the matrix equations and then we use the like we're doing like Newton-Raphson and then doing implicit function to get the derivative information through that step. I don't know how familiar you are with all of it. The main takeaway is like we're not using like sparse linear algebra as we should. Like if you really wanted to go to like 1,000 node networks, the admittance matrices, the connectivity, it's all very sparse. And we're not actually taking advantage of that sparsity in our implementation right now.
So is the power flow, is that something that you're trying to do like day ahead, or is that something that you could know about a system like and then use those for a larger period of time? And you're trying to figure out your data.
Yeah, so right now we've started just by looking at static dispatch. Looking at like the dynamic dispatch problem is just harder because you're like multiplying the problem size by like the number of time steps. That's something that I think part of that is like the scaling problem. There are also like additional interesting factors there of like you add the constraints on your generators and like how fast they can ramp up and down. You add uncertainty from like generator capacities due to weather and things like that. That's a really interesting problem. A mix of like there are new things that we need to do to like handle that extra complexity and like the scale is going to increase.
Do you have a sense of the complexity of like implementing this in a methodology and different like grids, geography or complexity of system?
Yeah, so I think that there are kind of two ways that a tool like this could be used. One of them is for like offline ahead of time analysis, where you want to generate like a library of these different failures, and then you could refer back to that library when you're doing interconnection studies or when you're doing your dispatch or all of these things. And that's something where you could like use some like really large computer, like just have it run for a week and like get your solutions, and then you use it over and over again. Another possible application is using this like at runtime. So like if you're trying to clear a day ahead market, try to solve this problem to test the reliability of that solution. Or maybe even if you're running this like online as a decision support tool for grid operators, then you have much like tighter requirements on how fast it's going. I think that one of the challenges will be like managing your system boundaries well. So if you have like as much time as you want to do this offline computation, maybe you can handle a large circuit or a large geographic region that you can cover. If you wanted this to run like online for decision support or something, maybe you would want to focus down on like just a distribution circuit or like just a set of distribution circuits, just to make the problem easier to solve in real time.
nobody will have a second.
Yeah.
What's the state of like synthetic data for the powered flow? Because obviously this like data availability is a huge constraint on anybody doing this research. Like
Yeah.
what is the state, of just sort of synthetic or other ways to crack some of the problems of testing this on real life grids and loads without having sort of years-long data negotiations?
Yeah, I think that is like from what I understand, it's a huge problem like throughout power systems research, especially like at the systems level. I know there are like large research groups where all they do is they do like synthetic grids. So like I talked to some people at Texas A&M where like their project is like their research project is they just like generate synthetic grids that are similar enough to the Texas grid, but not actually revealing any private infrastructure information. Those test systems I think are really important. Like we use the IEEE test systems for our examples. And when we look to like scale up, we're going to be scaling up to larger synthetic systems. I'm not too familiar with like the gaps between those synthetic systems and the real systems. They seem to be pretty standard, but maybe you.
I'm not. I guess the other question is, can you represent a grid in some more coarse way that makes the problem easier to solve while say identifying like a subcircuit and you don't know where in that subcircuit the fault's going to happen, but can you sort of mesh things together to make the graph more simple to be able to optimize graphs in real time?
Yeah, that's a good question. There might be some like network reductions that you can do. Like the first step, which we are kind of doing here, is like if you want to look only at a transmission level, you kind of like group everything behind a substation into one load and just like treat that as your load for modeling purpose. There might also be like interesting network transformations that you could do at the transmission level to like group lines together and do this analysis. Maybe there's also like, that could be interesting to think about some sort of hierarchical approach where you start by like grouping everything together as much as possible. You find a failure and you like zoom in on that area and then try to find a new failure and do that repeatedly until you get something fine-grained. But I think there's a lot of interesting stuff to talk about there.
And then I think we covered some of this already, but I'd like to hear more about kind of what you have in mind for the next steps of the research, any of the big questions that you want to answer that you know, as a result of this.
Yeah, that's a great question. It's something that I'm still trying to figure out. It seems like the big question that everyone, or a lot of these like system operators are talking about is like, how can they balance the reliability of the system with like, a lot of these system operators, they're faced with like increasing renewables penetration. And to them, that's essentially like taking their hands off some of the controls of the electric grid. Like they're very used to the situation where like they can just, you know, turn a dial or make a phone call and someone like increases production at a gas or hydro plant. And now like they don't have that power anymore. So they have more limited control authority, but they still need to maintain the reliability of the system. One thing that I'm really interested in is we have a lot of tools in robotics for dealing with these systems where you have very limited control authority. So like say you're trying to steer a glider through various wind currents, you're not able to control everything about the glider, but you still need to make sure that it's robust and doesn't crash even when there's turbulence. So we have a lot of interesting tools for solving that sort of control problem, for balancing this lack of control authority with these needs to have high reliability standards. And I'm really interested in like exploring how much of that can transfer to some of these grid control and operations problems.
I was going to say on that front, from more of a policy side, it seems like this would be a really cool basis for some sort of demand side response market where you identify which commercials to pay ahead, where the potential sources of failure are, and then identify commercials that are bidding power that the demand is really cool. That seems like a really cool basis for that.
Yeah. Yeah, I'm also really excited about all this like demand response and peak shaping stuff. I think it's a really like high leverage way to like get a lot of grid upgrades, like a lot of grid resiliency out of like relatively small things.
In the same way, storage siting evaluation as well. Right.
Yeah, I think storage siting, that's also like a good application is like you can find like where are there vulnerabilities, but you could also do something like where is there likely to be congestion like you probably have historical data on where the congestion is, and then you can cite your batteries to like get better exposure to that congestion or to like variability in the marginal price. I think that I've talked to a couple of like battery developers, and it seems like they do look at that pricing stuff, and they have pretty good access to data on pricing. It seems like one black box for them right now is the distribution level. There's not as much access to operational data or demand data at a like below the circuit level at distribution, which they seem to be interested in for citing batteries as well.
Well, since it seems like there are no more questions, we can just go ahead and end this here. Thank you so much, Charles, for that.
Great.
Yeah. Your contact info is up there.
Yeah, my LinkedIn, so feel free to reach out. I'm also like on MIT Slack, which might be easier. Yeah, it was really great having this conversation. I'll, depending on the time, I can stick around until 1 p.m. and happy to have more conversations.
Most of the time.